The Sky This Month with your host, Dave McDonald.
Hi, welcome to The Sky This Month, September 2020. I'm your host, Dave McDonald. September is a great month. We have Jupiter blazing in the night sky as you look towards the south, and the Juno mission is at Jupiter, and I have as a special guest Dr. Fran Bagenal, who is a co-investigator with NASA's Juno mission at Jupiter. You're going to love that interview. First, a few other things that are going on during the month. So I want to mention that we have an aerospace festival that is happening at the McAuliffe Shepard Discovery Center on Saturday, September 12th, 10:30 to 4 o'clock. Get the details at www.starhop.com. And then we also have on September 26th, International Observe the Moon Night. Everybody around the world is going to be looking at the moon at the same time. I hope there'll be a special event at Belmont High School from 7 to 9. So check out the event calendar. You see the address at the bottom of your screen there to check out where and when events are happening. So mark your calendar for September 26th. At the end of the show, I'm going to talk about the moon and Mars, the autumnal equinox, Mercury and Spica, Jupiter, Saturn, and the moon are going to be together for 3 different nights, and I'll talk about those towards the end of the show. As I mentioned, Jupiter is blazing in the southern sky, and right now we have the Juno mission that is at Jupiter. I'm going to show you a video about the launch of the Juno mission, and then I will be showing you and introducing to you Dr. Fran Bagenal. So enjoy this launch, and then Dr. Fran Bagenal.
The Atlas V 551 rocket, weighing 650 tons, launches and reaches a top speed of 4,500 miles per hour. The rocket hurtles through Earth's atmosphere, exhausting its fuel and reaching orbit in just over 10 minutes. The payload fairing falls away, revealing the Juno spacecraft within. Once in its proper orbit, the Centaur booster gives the probe its spin and sets Juno free on its journey to Jupiter.
Well, it gives me great pleasure to introduce our guests for this month of September. As you know, we have Jupiter is blazing in the southern sky at night, and Dr. Fran Bagenal, who's the co-investigator of the Juno mission, which is currently investigating Jupiter in orbit around Jupiter. And we welcome Dr. Bagenal to our program.
Pleasure to be here.
It's so good for you to take time out of your schedule to be on our show. And so just to start with, I have a poster, which I'll show, that says the history of our solar system is found in the formation of Jupiter. So I was wondering if you might tell us a little bit about that. What is Jupiter? Why are we going to Jupiter? How are we going to Jupiter? About the spacecraft orbits and things of that nature.
So let's talk a little bit about Jupiter, because in fact it's about 320 times the mass of the Earth and about 11 times the radius, and it's really big. And when you spread it out like this in a map, you see these belts and zones. You see the great red spot that's been around for a very long time, centuries. But the question is, what are you really seeing? What is it? And what I want to show you is that it is, let me just go on to the next slide. What we're really looking at here are clouds, okay? And most of these at the very top layers are ammonia clouds. There's a little bit of coloring. We don't really know what causes the coloring, but tiny amounts of different compounds can make it go darker, and it hangs around for a longer time. It gets darker and darker, more and more orange. But that may be partly sulfur, because the next layer down is a mixture of ammonia and sulfur. And then below that, we think there's a whole lot of water inside. Now, the reason why this is important is as following. If we think about how we think the solar system formed, we think there was a star at the center, it cooled off, and then there was all this gas around the star. And of course, it'll be hotter closer to the star and cooler further away. And so you're going to have rocks and metals condensing out in close, making the terrestrial planets. And there's not a lot of rocks and metals in the universe, and so you get fairly small planets. But there's a lot of oxygen. You add oxygen and hydrogen, the most abundant element, and oxygen is the third most abundant element. So hydrogen, helium, oxygen in that order. And you mix in, if you take hydrogen and oxygen, you get water. And beyond some distance away from that star, you begin to have ice forming, ice making big snowballs, and that makes the core of the giant planets. So you can see, knowing where the water is and how Jupiter formed is a key part of understanding our solar system, the formation of our solar system. So we want to go with Juno to go and understand what it's like inside, and that will help us understand the formation of Jupiter and the formation of our solar system. So that's why it's key and why we're going with Juno.
Nice.
So let me just tell you a little bit about Juno. This spacecraft is very large, and if you look at this diagram here, down here is a human to scale, right? So it's really large spacecraft, and we're using solar power. So these big panels are solar panels, and they produce about 500 watts of power. And it's
like you could drive a car down the solar panels.
It's about that size. Yeah, it's about that size. Good point. They are spinning. It keeps the solar panels pointed towards the sun, obviously, and it keeps the antenna here pointed towards the sun, and the Earth is close to the sun, so you keep it pointed towards so we can communicate with the spacecraft and it can communicate with us. And then we have a bunch of instruments that make measurements of the magnetic fields, of the charged particles. We look at Jupiter in a different wavelengths, and that tells us about different parts of the atmosphere. So microwaves look deeper down where it's hotter. We measure the microwaves that are coming out from Jupiter because it's hot inside. Hot material emits microwaves, and what we're looking for is to find the water. We want to look for absorption of microwaves. So we all know you heat your water by putting it in the microwave, and because water absorbs microwaves. So we can look for the absorption of those microwaves to tell us where the water is. Now we also look in UV, ultraviolet light. We look in the infrared with this spectrometer, and we have a camera on board, one little camera that takes visible images. So those are the instruments that we have. And what we do is we are in orbit around Jupiter. And it's a rather strange orbit because it's 53 days long. So normally things that orbit the Earth, they take maybe 90 minutes to go around, you know, the space station, things like that. Here we have 53 days. And so it takes a long time out here. And then when it comes in close, it zooms over the North Pole and out again. And we've done this 28 times in the 4 years we've been in orbit. And when we get in close, we have to be very careful to keep clear of this donut of radiation, energetic particles trapped in the magnetic field. So we go from pole to pole. And because we're so close to this 320 times the mass of the Earth, we're moving really fast. The gravity of Jupiter is really strong. So we zoom from pole to pole in 2 hours. And so we go above the clouds under the radiation belt. And over time, our orbits begin to change. And by about 30 few, we'll start going into the radiation belts, and we have to be a bit careful. So that's the key issues of our orbit and what we want to see, and why we're sending Juno there.
Well, that's great, and it's so neat. And also, just as an aside, I know I took one of my STEM classes to a place called Carbon Nanotech down in Merrimack, New Hampshire, and it turns out that they made some type of carbon nanotechnology that is part of the shielding to protect the spacecraft and
right.
students. So
yes. So we have to put all the electronics in a box and shield it with this this technology to keep the radiation out. Exactly. Yeah. Good point.
yeah, and so that's a neat connection to the mission from New Hampshire. So tell us, Dr. Bengonal, how we have what have we learned? We've got that camera, which I understand was not necessarily in the original plans, but it was kind of like, well, the public demanded to have a camera.
Yes.
But tell us what have we learned? What have we found out since the Juno mission?
So let me show you some of the things we're seeing. So what's interesting is we have this camera, and we put it on mainly, we call it the people's camera because it's really, everybody can access the data and play with it and do things. So if you go to this website and you click on JunoCam, you can go and look at the images. We as soon as they come from the spacecraft to Earth by the radio transmission, we then post them on the website, and people can download them. They can play with them and do what they want, and then post their ideas back up. So if you look at the pictures in true color, what your eye would see is, if you are actually on the spacecraft, it doesn't look all that exciting, does it? No, it looks like you see a little bit of cloud, and you have to look carefully to try and see something. But what you can do, and this is what the citizen scientists are doing, is to take the image and you go into Photoshop or whatever your favorite application is, and you crank up the color contrast, and you get things like this. Really cool images with the contrast showing you the structure of the atmosphere. And we're getting up close, and so we get a real detailed image of the structure and so on. So this is one of the pictures that we've taken. But some people do art. They take the images and manipulate them in a whole variety of very imaginative ways and then post them up. And so this is one of my cool ones. It's just a sort of Van Gogh application to Jupiter. And so the creativity of the general public is enormous, way more than the scientists. And they're doing all sorts of really cool stuff. So that's the art side. The citizen science side is looking at the atmosphere. And what they're seeing are all sorts of things in the atmosphere, particularly dynamics. And so you can see here a lot of turbulence. You see storms, these ones going around. These are, in fact, many times that big record one, which is about to hit Texas and Louisiana right now. We have Jupiter. There's lots and lots of those storms in the atmosphere. So because we're spinning every 30 seconds, we can't really stare and take a movie, but we can take clips every spin and put those together in various ways. So the strip along the top is a view from flying from the north through the equator and back out the South Pole. And then we put together images of the poles like this. And we're seeing for the first time the poles. So we put together a few of those, 2 or 3 of those images, and now you can see the structure of the polar region. We've never seen this before. Juno is the first time we had a chance to see this. And so you're seeing these vortices around the poles in this visible light. And the poles are blue, we think, because of the same reason our atmosphere is blue. It's scattering, Rayleigh scattering by molecules in the atmosphere of sunlight. Whereas the red around the equator, we think, is actually red clouds that have been reddened by a small amount of sulfur or some other compound in the equatorial region. So we're learning about the difference between the equator and poles for the first time. Now, if you want to look in more detail at the atmosphere, it really helps to look in the infrared. And so here we have an infrared image of that shows you sort of between the ammonia clouds, you can look deeper, and it's hotter deeper, and so you see the infrared light coming out, right? So this isn't reflected sunlight, this is glowing heat coming out between the clouds, and you can see it. When you look at the poles with this camera, this is what you see. It's amazing, the North and the South Pole, and you see these storms around the central pole. So the pole is right here, and you can see in the south we have 1, 2, 3, 4, 5 storms, and in the north we have 1, 2, 3, 4, 5, 6, 7, 8. So they're different. North and South Pole not the same. We don't
interrupt and ask, which
yeah.
of the colors, the yellow or the darker red, is the hotter, or what's the significance of the coloring?
Excellent, very good question. So the more white, yellow, lighter colors is hot, and you're looking deeper, and the darker colors are cooler, and you're looking higher. So you can see in these storms, it tends to be the center of the storm is higher up. So you can think of these storms going around, and the center is higher up and cooler, right? And that's what we're seeing at the center. And then around the outside, you're seeing the structure around it. Yeah. So these are the poles that we're seeing, and the number of these vortices has stayed the same in the south, and actually it's changed in the north. And over 4 years, we've had some changes. But not very much. I mean, they're pretty persistent. Unlike the Earth, where the weather changes hour by hour, day by day, at Jupiter, it tends to be more a year to year before it changes. It doesn't change very often. And we do see changes, but it takes a long time for the weather system to change. Remember, there's no land underneath. There's no continents. There's no surface that you can walk around with. These are gas giants. So you don't have the weather systems interacting with mountains and making the weather systems we have on the Earth, right? Yeah. So that's why they can keep going. There's no friction to slow it down, if you like, going over land and the ocean. Okay, so that's the red spot. Now, what's important is that Voyager saw the Great Red Spot, and it was twice the size of the Earth at that time. It's been observed for centuries. You can use a relatively small telescope or binoculars and see it. It's quite easy to see the Great Red Spot from your garden, and it's been observed since Galileo and others started looking at the planets with early telescopes. But what's interesting is that back in 1979, when Voyager was there, it was bigger. And what we're seeing is it's shrinking. We've been looking with telescopes from the Earth, and it's been getting smaller and smaller and rounder. And if it keeps shrinking at this rate, 2050, it'll be gone.
Wow.
Or it might just get bigger again.
After hundreds of years, and all of a sudden we are kind of the people that may see it go away.
Maybe. Or maybe not.
Not.
You know, maybe it'll get bigger again. We don't know. And so Juno is looking at the structure and seeing all the dynamics, the turbulence you can see around it. Sometimes the Great Red Spot swallows up a little spot that goes by. So you add to the dynamics and so on. So this is really raising questions about how does the atmosphere work? How does it evolve? and what's driving it. So we're also looking at the aurora. So these are the northern lights and southern lights. North is on the left here, and right, and this one over here is the South Pole. And in the UV, these are all false color, of course. So in the ultraviolet, what we're seeing is the hydrogen in the atmosphere being excited and made to glow by electrons that are bombarding the atmosphere. Same sort of thing as the northern lights and the southern lights on the Earth, aurora borealis and australis on Earth, where particles, charged particles, electrons come in. In the case of the Earth, you're exciting nitrogen and oxygen mostly and making them glow green and red. But at Jupiter, it's mostly ultraviolet light that is making it glow, and we can see all sorts of structure. And the infrared, which is the picture at the bottom, we see a lot of structure as well, a lot of dynamics, and we're really trying to work out what causes the instabilities that drive the electrons to go barreling into the atmosphere and excite these aurora. Because we're actually flying through the regions above the aurora and measuring the particles that come in and hit the atmosphere. Nice. We also, by flying close, we get to see the magnetic field. And so here we see the complexity of the magnetic field. So this is a diagram made because the spacecraft flies right through and measures the local magnetic field. And what we're seeing is a lot more structure than we originally thought.
And it looks to be a lot larger and stronger than what we have at Earth?
The magnetic field is a lot stronger than we have at the Earth. Because Jupiter is so much bigger, remember, 11 times the diameter, so really big in size. It has a very large dynamo region inside, which is driven actually by hydrogen. At high pressures, hydrogen acts like a metal. And so you can generate a dynamo in that electrically conducting region inside and generates this very strong magnetic field. Yeah, it's the strongest magnetic field in our solar system. And we're measuring the complexities. And that'll help us understand the dynamo and how the magnetic field is generated in these giant planets. And
the hydrogen, metallic hydrogen, is that what's happening on the interior of the planet?
Yes. So when you go look inside, and in fact, that's just exactly what I wanted to show you next. We can use the microwaves to look below in the upper layers of the atmosphere, but we use gravity data. So we fly over and measure the effect of Jupiter's irregular gravity on the spacecraft, changing the motion of the spacecraft a little bit as it flies over. We measure that very carefully with the radio signal, and that tells us what the distribution of mass is like inside. And so what we've learned is that the simple picture the textbooks have, where you have heavy elements at the center of Jupiter, hydrogen, and then molecular hydrogen above, simple, discrete layers, is not so true. In reality, things are more mixed up inside. And so those heavy elements that made the core, so the oxygen in the water that was formed the core, as well as bits of metal and bits of rock and so on, it seems like they've mixed up with the hydrogen. And this metallic hydrogen region in the middle, you can see this orange region, it's a very large region if you think of the sphere, is where the dynamo is generated. And then above that, you have molecular hydrogen, regular hydrogen, 2 protons and 2 electrons going around together, attached. And then we've got this layer where we have helium that seems to be raining out. Helium being the second most abundant element. It's about 4% of the mass of Jupiter. And we have some evidence again from the gravity that it's probably settling out from the outer layers. So we're learning that the inside's a bit more complicated.
Do we have an idea of what the dense rocky core, what elements make that up?
We don't know, we can't measure that. We can get a theoretical models. What you can really do is you can measure by looking at the sun, by looking at other stars. We can estimate what the cosmic abundance or the abundance across the whole of our solar system is of different elements. So you obviously have a lot of hydrogen, bit of helium, then oxygen, and then you get smaller amounts of other things. So calcium and magnesium and iron and all these things that we all know from the periodic table, but they're very small by comparison. And so we can use that sort of cosmic abundance of elements and say, well, let's have a theoretical idea of how this disk from which the planet's formed, what was it made of? And our guess is that the center of Jupiter, which is where this dense core is of heavy elements, is probably about 15 to 25 Earth masses, okay? So remember, the whole of Jupiter is 320 Earth masses, and so what we're saying is something like 20% or so, more or less, of that mass is in the heavy elements of the core.
So that's awesome about what we're doing at Jupiter, and what's going on next. What does the rest of the orbits or years left for Juno look like?
So we're flying through the magnetic field, measuring the aurora, measuring the clouds, measuring the atmosphere, trying to work out what it's like inside. And we've had so far, like I said, 28 orbits. And we are going to do a whole bunch more. We hope to get some money from NASA to continue. And with luck, we'll keep doing it for another 5 years.
Well, go Juno. Thank you so much, Dr. Banganel, for joining us. Hope you enjoyed that interview with Dr. Banganel. Amazing things happening at Jupiter. Lots of things happening in the night sky for you to enjoy, and I want to share some of them with you. To start with, September 5th, which is right at the beginning of the month, but we're talking 11 o'clock at night. You can see the moon and Mars ever so close together. As a matter of fact, at midnight, they're going to be even closer together. And the moon and Mars happen to be where the tails of the fish are tied together in the constellation of Pisces. This is the constellation of Pisces. Off to the left is the constellation of Aries. That's September 5th. The autumnal equinox is September 22nd at 9:31 a.m. I took the blue sky away so you can see the sun against the background of the stars. This red line is the ecliptic, which represents the pathway of the sun throughout the year. And the blue line is the celestial equator, which is a projection of the equator on Earth against the sky. And when the sun, which moves along the ecliptic, crosses the celestial equator on its way heading south, that's the moment of the autumnal equinox, the moment of fall at 9:31 a.m., September 22nd. And then later that same night at 7 o'clock, just a while after sunset, you can see the planet Mercury along with the star Spica, which is the brightest star in the constellation of Virgo. And they're hugging the horizon, so you may need binoculars to be able to see Mercury and Spica. For days after the 22nd, you'll still be able to see Mercury really close to the horizon. Binoculars will help, but you got several days after the 22nd to catch Mercury. And as I mentioned, Jupiter and Saturn blazing all month in the southern sky. This is where the moon is located on the 26th, which is International Observe the Moon Night. Back on the 24th, the moon will be closer to Jupiter. And on the 25th, the moon will be closer to Saturn. Hope that you can make it out to some of these events. Aero Space Fest at the McCall Shepard Discovery Center, September 12th. And hopefully at Belmont High School, we'll be having an event, but check out that event calendar on September 26th from 7 to 9. So great things are happening, and I hope that you enjoyed the show. I'm Dave McDonald for The Sky This Month.